Alright, so we ended yesterday with our list of forces. So you have all these copied down, so you have a nice reference to go back and reference them when you need be. Now, the activity that I handed out to you, number 3 through 12, they're little word problems describing a situation. Okay? Now, for each of those situations, you would need to draw a diagram and the applicable forces with estimated force values. And we'll talk about that in depth more here in a little bit. However, let's talk about some hints in doing these. You guys don't want to write them down, of course. So when you're doing these, first thing you want to do is obviously read the scenario and then underline your verbs or highlight them, or
so we can write on this page.
Yes, you can write. But you're going to want to put these in your notes, because there's a whole series of them. The next thing you're going to want to do is, based on that situation, you want to draw your diagram. Now I realize that not everyone in here is going to be super awesome drawers, but that's fine. Okay, stick figures are perfectly acceptable. Just as long as the overall theme is legible, it's fine. And of course, we know that our size of our arrows equals the size of our forces. Yes, Nathan?
I was thinking, like, you know, the other day when you were pushing against the wall?
Yes.
Like when you were leaning against it. If you were pushing an object into a wall, and if that's the wall and you're pushing, does friction still count there?
Technically, yes, but we wouldn't label it. It would still be, I mean, you know, theoretically, anytime an object is touching another object, there's going to be friction. But the only time that we are going to label friction if it is a horizontal, if it is moving along a horizontal surface, okay, or moving along a vertical surface, but it has to be moving adjacent to. I guess that's the best way to think about it. So when you do these diagrams, the first thing, and I'll do an example of this, the first thing you'll want to do is to figure out your force of weight, okay? Estimate your force of weight. And then based on that, you'll come up with a scale. Like 1 centimeter equals however many newtons. So you can fit these drawings on your graph paper. After you do that, then you can draw your force of weight arrow. Okay? So that should be the first thing that you draw. Your first force arrow should be your force of weight. When are you not going to have a force of weight arrow?
When something's not suspended.
When something is not suspended. It will not have a weight? Is it always going to have a force of weight? That was a trick question, right? It's always going to have a force of weight, unless we're dealing with space, which we won't be. Okay, so it's always going to have a force of weight. So that's the first thing you should draw. Now, when will it not have a normal force? Because there are situations it won't have a normal force.
When it's sitting on a table?
When it's suspended, when it's hanging. Okay? Remember, a normal force is when an object is sitting or resting on an object, on another object. Okay? So suspended, right? Swinging, hanging, whatever, that will not have a normal force. When else? Yes? When you're free falling. Very good. So hanging and free falling. Those are your non-normal force diagrams. And then finally, remember, after you draw your force arrows, you need to label them with what type of force. The hanging force, is it a tension force in that case? Is it a push force? Is it a friction force? What type of force is it? And label with how many newtons, the magnitude. We're going to skip ahead a couple of these. You can watch in slow motion if you want to go over this. We're going to stop here. Okay? Now, it's not necessary to draw these. All right? We're just going to do these as a class. All right, so we have this object. Whenever you're looking at these, the first thing you need to do is take note of the net force. In this case, is 0. Net force is 0. So what does that mean?
It's not moving.
Not moving? Is that what you guys were saying? Okay. What else does that mean?
That's 400.
Okay. Well, let's think about that. Does it have to be 400 newtons? No, it doesn't have to be. That's a good question. Why not? What else could it be? What? Yes, that's right. It could be 300. Yeah.
Because there's friction,
Okay.
and because it wouldn't necessarily have to be 400 newtons.
Why? Claire, what do you think?
If the friction is greater than the pull, it's not going to move.
That's right. So if the friction is greater than the pull, then it's not going to move at all, right? So what would be a better value to put for the friction or the force pull? Less than 400, right? Or equal to, yeah. Right? Does that make sense? Remember, friction is the resistance to change. So you have to get at least over 400 for it to move. But anything under than that, it's not going to move. Okay? Good? Moving on. Let's try this one. So this one, which, look at our net force, we have 20 newtons to the right. So here's the easiest way to do this is to recognize that whichever direction you're going, that value has to be larger than the other direction, right? Than the other side. So in this case, the right side has to be larger than the left side, right? The top and the bottom just cancel each other out, so they're negligible. So what do? What's our answer for force pull? 420 newtons. Right? Yeah, to the right. And that answer's right. Which direction are we going?
Right.
So which side is going to be bigger?
Right.
Right. What's our answer?
Yeah, 290.
290? This time we subtract, right? Good. What about this? Which direction are we going? Down. So which one's going to be bigger?
Down.
Down. The weight?
180 newtons.
What's it going to be?
180 newtons.
Right? Okay, good. With that being said, look at number 3. 1 and 2 are just like what we did on those slides. Number 3, it says, the book is at rest on a tabletop. The free fall or a free body diagram for this situation looks like this. So, what is the book doing? It's resting, so that's what you're going to identify. First thing is identify it's resting, so underline rest. Next thing you're going to do is draw your diagram. And what is that book doing? Resting on the tabletop. Oh wait, we need to do. Okay, there's my whatever 30-second book on a tabletop. Now, what do we need to do first? Or next, I should say, Nathan. Okay, label forces. So first thing we need to do is come up with our forces. So I'm going to come up with my force of weight. Now, this is going to be up to you when you do these. Another thing you need to take into consideration is that you want these force arrows to be relatively small when you're drawing them. You don't want to have to take a bunch of graph paper together to draw a meter-long force arrow. So, small book. Let's make it a small force. So, what is my force going to be?
100.
Okay, 5, 1. We'll split the difference and make it 2. Okay? Now, my scale. I'm going to say 1 centimeter equals how many newtons? 1 newton. Sure. Okay. Remember, this is up to you. This is your decision when you're doing these. But try to make it as easy on yourself as you can. So, what is our first force arrow?
The one
Force of weight. Okay, always. It should be force of weight. How long is that force of weight arrow going to be? 2 centimeters. So I'm going to get out my ruler and I'm going to measure 2 centimeters. And that happens to be 2 centimeters according to my ruler. According to me. And I'm going to label it. My force of weight equals 2 newtons, right? What else do I need? A normal force to oppose it, because it's sitting on the table. So, how long is my normal force arrow going to be? 2 centimeters. Or Fn equals 2 newtons. That's 2 centimeters. Last thing, and I want you to write this on your paper underneath those directions, is put add force net. Your net force. Add force net to each diagram. Do we need to add horizontal, left or right forces? No, because there are none. What is our net force in this diagram?
0.
0. Okay. Questions on that? Okay, let's look at number 4. It's saying a girl is suspended from a bar which hangs from the ceiling by 2 ropes. Okay, like a trapeze. So, first thing I want to do is, what's my force weight of the girl going to be?
15 kilograms.
Okay, put in newtons up.
115.
Thank you.
150 newtons. That's actually pretty big. Yeah, let's just go with go with 100 newtons at most. It's still pretty big. We're talking about a girl. Well, whatever. 150 is fine. Whatever you want, that's fine. We're not going to negotiate or bicker about your Newton value, just as long as it's relative. So, can we use our 1 centimeter equals 1 Newton?
No.
No. Right? Or else it would be a meter long, and you'd have like a super fold out piece of graph paper. So, what am I going to do? I'm going to say 1 centimeter equals how many? 25, 50, sure, whatever. 50 newtons. So that means I'm reducing my arrows down to just 2 centimeters, right? My girl and trapeze.
I think it'd be a trapeze.
No clue.
My 10-second. She's wearing a leotard. So what do we have? We have force of weight, right? What force is pushing up or pulling up? Say. Tension force. How many?
All of them.
No. How many tension forces are there?
Oh,
2, right?
Yeah.
How much each?
50.
50 newtons each. Half. So how long are the arrows going to be?
1 centimeter long.
1 centimeter long. Yeah, half of what the other one was. Okay? That give you some idea? Good. So the rest of these you'll be doing